Welcome everyone to the Accellera virtual lunch presentation. My name is Lu Dai. I am Accellera's Board of Directors Chair. Our lunch event is in 3 parts, with the first being a short update on Accellera, or an introduction for those who may not know too much about us. This is followed by a brief Accellera Technical Committee update by Martin Barnasconi, our Technical Committee Chair. The third portion of the event will feature a focus on our newest working group, the Functional Safety Working Group, with an introduction by Alessandra Nardi, its chair. She will also moderate a panel discussion that will conclude with an open Q&A session where you can submit written questions that she and her panelists can answer. Again, thank you for joining us today on your DAC lunch break. I'm going to start our presentation by giving you a brief overview of Accellera first. Accellera is the leading international standards organization in the pre-silicon design and verification. Our mission is to provide a platform in which electronic industry can collaborate to innovate and deliver global standards that improves design and verification productivity. We have a long history of successfully delivering leading pre-silicon design and verification standards, starting from Verilog and VHDL back in early 80s, to System Verilog, System C, UPF, UVM, IP Exact, System RDL, and more recently, Portable Stimulus. Accellera has its backing from broad industry support, including many leading semiconductor, IP, system, and EDA companies. Our membership is composed of 10 corporate members, 30+ associate members, and 3 startup and university members. As a member, you could join the development of our newest standards and get early access to leading-edge design and verification technologies. As corporate member, you could initiate and drive a standardization process. For the IP and system companies, your membership allows you to ensure the new standards meet your company's needs, as well as influence EDA companies in their implementation priorities. For the EDA companies, membership allows you to develop product that will meet the general market with a wider pool of beta testers and potential customers. Accellera has many working groups operating independently under the guidance of Board of Directors, and as its proxy, Technical Committee Chair. Many of the standards that went on to receive IEEE standardization no longer have active work within Accellera. However, from time to time, IEEE commissions Accellera to drive some of the update activities. Some of the mature standards without IEEE standardizations may become dormant over time. Currently, the active working groups consist of multiple System C-related working groups, IP Exact, and UVM, that continue to supplement IEEE activities. AMS working groups, such as System Verilog AMS, System C AMS, UVM AMS, the Interoperability Working Group of Multi-Language Verification, and the newest Portable Stimulus, IP Security Assurance, and Functional Safety Working Groups. Here's a list of latest Accellera standards hosted on our website that are available for download. In addition to language reference manual and user guides, we also have examples, reference implementations, libraries, and regression suites available. Here's a list of Accellera standards that went on for IEEE standardization. With Accellera's corporate level relationship with IEEE SA, all these standards are available to you for free download through the IEEE GEP program. As new Accellera standards receive IEEE standardization, more will be added to this list. Last but not least, we want to thank our global sponsors of Cadence, Mentor, and Synopsys for making this presentation possible. Again, thank you for joining us today. And now I would like to hand it off to Martin Barnasconi, Accellera's Technical Committee Chair, to share some brief information on Accellera's technical committee.
Thank you, Lu, for introducing Accellera and explain its mission, working groups and activities. My name is Barnasconi. I am the Technical Committee Chair of Accellera and responsible for the coordination of all technical standards developments which are done in the various working groups. In today's meeting, we will zoom in on the standardization plans and activities conducted by the Accellera Functional Safety Working Group, highlighted in yellow in this picture. It is the most recent working group we started in Accellera. Alessandra Nardi is the chair of the working group and Franck Galtié is the vice chair. As you can see in the picture, Accellera hosts many other working groups and standards, covering standards related to system level, design, analog mixed signal, verification, and standards for integration and infrastructure. Before I hand over to Alessandra to explain the mission and objectives of the Functional Safety Working Group, I will briefly explain the standard development process we follow in Accellera. To better understand the industry need and interest in a standardization activity, Accellera starts a so-called proposed working group to identify industry support for a standardization initiative. When we started this process for functional safety, we were overwhelmed with the number of companies interested to participate in such proposed working group. Alessandra and Franck organized the first kick-off meeting in December last year with an attendance of 50 participants representing 30 companies. The outcome of the proposed working group confirmed that there was a clear industry interest and commitment to develop a standard for functional safety. And it led to the formation of the Functional Safety Working Group in February. The main objectives of the working group is to develop the actual standards document, as well as promoting the standards development at events like DAC. In addition to the standards document, working groups could develop so-called supplemental material, such as an open source reference implementation, user guide, which help in the deployment and adoption of the standard. Ultimately, the goal is to transfer Accellera standards to IEEE for further industry adoption and use. Alessandra will now share with you more details what happened since the formation of the Accellera Functional Safety Working Group.
Thanks, Martin. Good morning and welcome again to this session focusing on functional safety. I'm very glad to have the opportunity to talk about the activities covered by the Functional Safety Working Group and the progress that we made so far. We're going to start with a brief 10-minute introduction to the working group. That includes some information on the history and the statistics of the team, the needs and the requirements that we gathered during the initial period, and then the mission and the goals that we finalized based on those. We're going to also cover how do we connect to the existing functional safety standardization landscape. And then we are going to close this introduction session with a short summary that gives an automation perspective. And then we'll move on to a panel of 5 safety experts from ARM, Renesas, Intel, NXP, and AMD. And each of them will give a short summary on the view that they have on their unique challenges and opportunities. At the end of both of this, we're going to have time for Q&A. The shaded blue line in this slide represents the timeline of the working group. So it starts at the left with the green coloring. That's where the team was a proposed working group. It was formed in October 2019. We have had our first face-to-face kickoff in Munich in December 2019. In this phase, the group is focused on the industry needs and confirming that there was enough industrial support, and specifically on gathering the what and the why. Okay, so what is needed and why it's needed. And in this portion, we had 36 companies and 90 members. This is no Accellera membership required, open to the community. After this, we prepared a document proposed to the board of directors. It was voted positive for creating the working group in February 2020. So that's where the real technical work started. And that's the phase where we focus on the how. How do we actually support the needs that we gathered as a proposed working group? And so that's what we're working on. Unluckily, our kickoff was supposed to be in person in Austin in March. We had to move it to a virtual kickoff, but it was 3 days of 3-4 hours discussion to get started on different activities and subgroups. In this phase, we have 26 companies, 89 members in the roster, and we have a plan of releasing a white paper in Q3 and also get ready for a Q4 public review. On the top right in orange, you see the stakeholder. The goal of this working group is actually to satisfy the needs of EDA, IP, silicon, and system providers. So let's spend a bit of time to recap what we heard from the community in terms of needs that they would like to see addressed. So one of the key points of the safety critical applications is that the development lifecycle is distributed. But the functional safety information does need to be exchanged between the different players of the supply chain. And so the need that clearly came out from our proposed working group phase was to have a holistic approach to facilitate the exchange and the traceability of information across the different players, but also across the different operations and work products handled by a single player. And in terms of the scope, there are different dimensions to the problem, and we try to capture many of them in these pictures that you see here. We talked about already the supply chain and what we mean by intralayer and interlayer, right? So the interlayer covers the communication across different players in the supply chain, and instead the intralayer refers to the connection between operations and work products within the same provider. And so an easy example that you can take of for the intralayer would be, for example, the interoperability across EDA tools. So the last column of these pictures actually lists examples of operations and safety work products. I apologize for the many acronyms and the small font, but the goal here was to actually give a quick gut feeling of why enabling the exchange of information in a formal way can really make a difference, because you can see the number of work products involved or the operations involved. The last two dimensions that we haven't covered yet are type of industry and the domain. And to maximize the benefit of this work, the goal of the team is to actually span across as much as possible of the domains of the EE systems, for example, the digital, the analog, PCB. And then also, even though the initial focus is on automotive and industrial, the goal is really to expand also to aerospace and medical. And then last but not least, during our initial discussions, we also realized that there is still a green field of opportunities actually in terms of development of methodologies to enable functional safety. And so we are starting with very clear execution goals, as you will see in the next slide, but we also want to keep the door open to any discussion that can come along. And we have called this our exploration goals. And just to give you an idea of what we're talking about, some basic examples can be, for example, methodologies and discussions related to the safety element out of context or to dependent failure analysis, and many questions that are still open about these two topics. So to address the requirements we just went over, this is how we capture the mission of this group. And I'm just going to read it here. Our mission is to provide a unified definition of the functional safety data to improve automation, interoperability, and traceability across the functional safety development lifecycle of electronic circuits and systems. In practice, this translates to two main immediate goals. The first one is to standardize the functional safety data into a data model. So the idea is that out of this data model, you should be able to support different use cases. And very basic examples of these use cases would be, for example, the generation of a quantitative FMEDA or the ability to carry over, connect information between an FMEA and an FMEDA. Now, the second goal is to actually develop a standard format or language to express the data model that we just described. Now, on the bottom right, you have the pictorial representation of what we just said. And the functional safety data is at the center to enable the different operations. And this is true for both intra-layer, so within a single provider. And you see the list of providers on the right, IP, EDA, silicon, and system, and across the different providers, the inter-layer. Now, in terms of what exactly is this data model, The way we envision it is an additional set of information which is specific to functional safety, and that would be defined and carried over together with the design verification information. It's pretty much like what we do for low power today. So these two on the left, right, the two buckets of data, the light blue boxes, are the ones that together will be able to support the development life cycle, or if you want to look at a very high level representation, the V model. There is a lot of fervent activity in the community around functional safety standardization, since so much more of the applications are now becoming safety critical. And one very important aspect for us in this group to keep in mind is to keep the consistency with the existing standards. Now, even more importantly, though, our focus is really on enabling the implementation of the existing requirements and methodologies that are linked to these standards. And so what you see in the left part of the picture, you see captured the traditional representation of the functional safety standards of the electrical, electronic, and programmable electronic safety-related systems. And those are all connected to the IEC 61508 meta standards in the middle. So as we said, the Accellera Functional Safety Working Group is focusing primarily on the three main pillars there: automation, interoperability, and traceability, with the goal to be referenced as state-of-the-art by the standards to the left. And the model is really similar to what has happened for example, the IEC 62380, which is the base failure rate calculation, which is referenced in ISO 26262. So very similar idea. One more point is that functional safety is also connected to other related activity. Examples would be SOTIF, the safety of intended functionality, the security, the AI-based safety, and there are many initiatives connected to these fields. And for example, we are aware of IEEE P2851 that is working on a landscape document that is covering and connecting all the satellite fields to functional safety. So with IEEE 2851, we have periodic alignment, and the work model is the same that Accellera and IEEE have worked over the year. And so once Accellera has completed the work, it will be transitioned to IEEE P2851 for standardization. Last point before we hand it off to our presenter is the automation perspective. So we have a very active participation from the EDA vendor community in the Accellera working group, and we all share the same belief that EDA can be a big help in the functional safety arena. So at the bottom of the slide, you see the representatives from the EDA vendor companies that are active in the working group. And not surprisingly, during our discussions, we realized that our perspective is very much aligned. We do see a big opportunity to utilize much of the existing EDA infrastructure and extend it so that it becomes functional safety aware. But of course, we also see the challenges of building the bridge on finding the common language between the well-established best practices in functional safety and the traditional, so to say, design and verification methodologies. Now, the great opportunity we have in this group is to join forces between the functional safety experts and the EDA community, not only to work on the standardization, but actually to combine it with automation. Now, when standardization and automation work together, you can, by construction, enable both interoperability and traceability, which are fundamental to safety-critical applications. Let's move on to our panel now. We have 5 functional safety experts, and each of them will share their unique perspective, challenges, and opportunities. So our first speaker is Ghani Kanawati from ARM. Ghani is the Technical Director of Functional Safety in the ARM System Group. And before joining ARM, he worked at Intel for a total of 24 years of experience. He has a broad expertise that covers functional safety, SoC design and verification, multiprocessor design, high-performance computing, reliability, and availability. Ghani holds a Master in Biomedical Engineering and a PhD in Computer Engineering, both from the University of Texas. Ghani, thanks for joining us, and you're up.
Hello, everyone. I hope everyone is doing well. My name is Ghani Kanawati. I will be talking about some of the challenges of IP designs that are used in function safety applications. The agenda for my talk is first I'll describe the position statement, then I will talk about the challenges, Then I'll talk about a few examples and end my talk with recommendation. We all know that IP and SoC designs used in safety applications are becoming very complex. Products have to satisfy different markets with different requirements, and the lack of advanced techniques for safety analysis and safety validation are increasing the complexity. The development safety life cycle of a product starts at the IP level, and then at the SoC level, and then at the system level, and conclude at the product level, which integrate the system. Fulfilling the safety requirements of the product requires that all pieces of the design fulfill their own safety requirement. This requires that safety information from one safety analysis and safety validation generated by one design hierarchy to be used by the consumer of that design to complete their safety analysis. Because of the enormous amount of information generated, communicating this information across all the development groups and companies can be challenging in terms of both the data and the format. Just imagine how much effort and time is needed to make this data usable by other groups having different expectations. Also, there's a need to agree on what information is needed to complete the work at each design hierarchy of the product. In addition, we also need to think of how to enable automation to make the data generated be used by a tool instead of being parsed manually. Also, different application and different safety standard that we need to satisfy can further increase the design complexity. For example, additional complexity can occur when the same IP design is to be used in multiple applications that might have different requirements. As listed in the slide, there are several markets that require functional safety. In addition to automotive, there's the industrial, healthcare, transportation, avionics, consumer. Each has their own safety standard. Some are very established standards, such as industrial, transportation, avionics. Others are not so. This can also complicate things because customers may have their own way of doing things and there is no agreement on common practices. Now, I mentioned a few times safety analysis, which is a requirement by any safety standard. Safety analysis is the process of analyzing the behavior of the design in the presence of systematic and random failures. There are several techniques for safety analysis. Some are quantitative, others are qualitative. Here, I'm only talking about one example of quantitative analysis. It's called FMEDA. It's a very commonly used technique in the industry. Failure stands for failure modes, effects, and diagnostic analysis, which is used to determine the effectiveness of the safety architecture of the design in detecting failures. We have to make sure that at each design hierarchy, the safety information generated, for example, at the IP level, can be used by the consumer of that design. For example, in this case, the SoC level. In addition, the designed IP may have to be configured or configurable to satisfy customer-specific requirements, which can also add another form of complexity when doing safety analysis. For example, do we have to repeat the analysis for every configuration? Also, since the design will be used across multiple applications, additional work has to be done to make sure that it covers additional requirements specific to that market or the safety standard of that market, which can also add complexity. In conclusion, design complexity and proliferation to several markets necessitate a different approach to current practices. Agreement on what safety information across the different design hierarchies, for example, IP, SoC, and system, and standardizing this information across the industry is required. Also, storing the safety information in data formats for the purpose of safety analysis automation is also required. For example, data generated by one tool should be consumed by another tool without any manual effort. Similarly, data generated from one design hierarchy should be consumed by another without any manual effort. This concludes my talk. I want to thank you for your attention.
Thank you, Ghani. Our next speaker is Riccardo Vincelli from Renesas. And Riccardo is the director of the Functional Safety Competence Center in Renesas, and with his team is responsible for the technical assessment of several Renesas products, including microcontrollers, SoC, analog ASICs, as well as software. He also led the definition of the Renesas card tool that allows the customization of FMEDAs. Riccardo has been involved in safety activities since 2005 for the development of Renesas components based on IEC 60730, IEC 61508, and ISO 26262. Also, in the last 15 years, he has been involved in several functional safety standardization activities, such as IEC 61508, ISO 26262, ISO PAS 19451, and UL 4600, and SAE safety groups. Riccardo, thanks for joining us, and you're up next.
Thank you, Alessandra. Thanks a lot for this introduction, and also thank you for having me today contribute to this interesting event. Benefiting from the introduction you already provided, let me jump straight into the core of my presentation. I would like to discuss today about the requirements for customization of safety analysis, required to comply with ISO 26262, but also relevant when dealing with the standards. In general, we have from one side the SOC supplier, that has to provide accurate analysis and results based on the assumed safety concept. On the other side, we have the integrator, that has to take the results from the supplier and adjust them based on the specific context being targeted. This customization is very important and cannot be skipped. It involves several aspects, and I wanted to focus here just on one of them related to the architectural metrics, as for example the single point flow metrics. For this, the following parameters must be adjustable by the integrator: the error fit rate, the element used as part of the safety concept, the impact of fault and failures, and the associated safety mechanism. Allow me to describe these points more in detail in the next slides. The component supplier provides the FMEDA based on an exemplary fit value. This may not be representative for the final product, due to the specific strategy, for example, adopted at system item level. Indeed, you do not want the fit of the several components of the system being based on different fit sources, without a valid justification. The mission profile for the final application may also be different from the one originally assumed by the supplier. Parameters as the temperature cycles do influence the results in fit rate. Again, the supplier will need to make assumptions about the elements in the component that may take part of a particular safety concept. This selection may not always match with the selection required by the integrator. We can split here, for simplicity, the elements into two groups. Application-independent elements. These are elements that are expected to be used in all applications. For example, the central processing unit or a possible internal voltage regulator. For this, the selection should be mostly fixed and not requiring adjustments. But what about if a component embeds multiple CPUs? Which one to select? Then we have application-dependent elements. These are the elements whose usage may be strongly dependent on the integrator needs. For this, the supplier may take as reasonable assumptions, but a level of customization is for sure needed. This will also include the selection of the pins, especially in components with high level of possible configurability. Note that this customization is also mandatory to comply with some of the verification reviews demanded by ISO 26262. One very important requirement is to customize how each fault or failure is impacting the final safety goal. Depending on the safety concept, the relation may need to be changed, impacting in turn the strategy for protection and then the resulting metrics. In particular, which fault may have a direct impact, which one may have an impact only in combination with other faults or failures, and which one will have either no impact or cause a transition to a safe state on its own. Finally, the safety mechanism claimed in the safety concept must be reviewed and adjusted for the final context. Here we can see different cases. Safety mechanism embedded in the component, where the configurability may be actually quite limited. Then we have a safety mechanism to implement or complement it through software. For this, the details of the final software have to be considered. Safety mechanisms then to be implemented at system level. For this, a strong dependency on the final product is expected. Refinement may include timing and coverage. Also to be careful when the results are blindly based on fault injection, as this might have a strong dependency on the context. So, as you can see, the integrator cannot just take the results from the supplier and use them out of the box. A fair amount of understanding and customization is needed to then represent the final context. From this point of view, usage of standard methodologies, clarifying also the information to be shared, and tools helping with automation are very key. This is why activity as driven by Accellera are very key. Thank you. Back to you, Alessandra.
Thank you, Riccardo. Our next speaker is Jyotika Athavale from Intel Corporation. Jyotika is a senior technical leader and experienced principal engineer. She's a recognized industry expert with in-depth technical knowledge of platform technologies and architectures for safety-critical systems, with a focus on functional safety and radiation effects modeling. In her current role at Intel, Jyotika is focused on pathfinding research on incubation technologies and strategies for avionics and automotive systems. Jyotika, thanks again for joining us, and you're next.
Thank you, Alessandra. This is Jyotika Athavale from Intel Corporation, and I can share a couple slides describing the functional safety challenges from an avionics perspective. If we take a look at the flight safety landscape, we are seeing an increased complexity, an increase in functional integration of the safety-critical avionics systems, such as flight control systems, flight navigation systems, cockpit display systems, or radar systems. And this is leading to an increase in demand for high-performance processors. Thereby, we are seeing a shift from single-core to multi-core processors. However, this introduces additional challenges with respect to certification, especially for the high design assurance levels such as DAL A and B. Also, with the shift to multi-core, we now need to consider new failure modes, and there are new requirements that need to be complied to in the DO-254 standard as well as in the CAS-32A. And especially while using COTS multi-core processors in these safety-critical systems, the other consideration is for size, weight, and power and cost, in addition to other reliability requirements such as extended life as well as extended temperature. On this slide, I describe some of the risks and challenges and considerations that we need to take into account as we work on the certification of multi-core SoC-based avionics systems. On the left there in the chart, we see an increased reliability risk due to single event effects. What we mean by this is failures due to radiation, so radiation-induced bit upsets that manifest as errors, and these could be transient in nature or permanent in nature. Some example of transient single event effects are SEU and SET, or MCU or MBU. And in the case of the permanent single event effects, we have single event latch up, single event gate rupture, and single event burnout. And these need to be mitigated, especially on an avionics system, because the risk is higher given the higher elevation. And as we know, the neutron flux, as well as the other particle flux, is much higher at those higher elevations, as you can see in the distribution in the chart. And also in the table there, we describe the radiation components as well as their integrated flux ratios, looking at 0 feet in comparison with the 36K feet. So it's pretty significant, and this is something that we need to consider as we plan our mitigations on that avionics system, looking at redundancy as well as dissimilarity, as well as other software mitigations on the system. In addition to reliability, there are other challenges such as new security challenges that need to be considered due to the increased connectivity, and this needs to be mitigated as well, considering mechanisms such as partitioning or isolation. On the bottom right, we are looking at another challenge, which is complying with the CAS-32A. And on a multi-core SoC, we do have shared resources such as shared cache, shared memory, and as we have multiple applications now running on multiple cores on the SoC, we will have that contention or interference. And as these applications compete for shared resources, there can be unnecessary delays or a risk of a cache miss. So these are things that need to be mitigated on the SoC, in the hardware that's on silicon, in the BIOS firmware, as well as the software, to reduce this mitigation and thereby ensure that we can meet the worst case execution time for the safety critical application, which should complete in a deterministic manner. So there's work that's ongoing to address all of these challenges and needs for the functional safety analysis and verification that we are discussing in the avionics use case subgroup in the IEEE 2851, which will also provide inputs to the Accellera functional safety working group activities via close collaboration. So thanks everyone, and I'm going to hand it back to Alessandra.
Thank you, Jyotika. Our next speaker is Franck Galtié from NXP. Franck is the Director of Functional Safety and belongs to the CTO organization. He's in charge of running functional safety within NXP. Franck, thanks for joining us, and you're up next.
Thank you very much, Alexandra. This is great to have the opportunity to share NXP vision on safety in this short talk. The complexity of autonomous mobility is dealing with the safety concerns and hyperconnectivity of the vehicle at the same time. Vehicles are capable of collecting data in a continuous stream from sensor fusion and using machine learning to make real-time calculation based on the inputs. The level of accuracy and precision in decision-making associated to assisted driving function is improving continuously. Today, we are not able to be more precise in autonomous driving, mainly because our technology limits us. We need that high accuracy. We have to develop more accurate sensors by adding imaging radar, for instance, by adding more sensors around the car in general. Obviously, with more sensors, we will have more data to handle as well. We will have infinitely more data going back into the cloud as well, that we'll need to be able to handle and use to continue improving the accuracy of decisions. The hyper-connected vehicle also needs higher level of cybersecurity to ensure the integrity of this data. At the same time, mediatization of driver behavior has created widespread consumer distrust. And there is intense scrutiny in the behaviors and decision-making of those vehicles. Our responsibility is to insist on the provision and inclusion of the most reliable safety integrity level product and systems, sensor technology, and AI/ML capability with functional safety. First of all, it's important to understand that the term safety covers two things: safety of the car functions, functional safety, and road safety, environmental and behavioral, through safety of the intended functionality, also called SOTIF. Today, standard exists for the first part, but is not yet ready for the road safety. One solution to this is NCAP. NCAP has established itself as a global reference for passenger safety, with Europe at the forefront. It's a very powerful toolkit that drives OEM to implement specific safety features. Its safety features roadmap can help inspire us to prepare for emerging trends. We can then make sure that these features always operate as intended or as needed. We cannot influence NCAP for sure, but we do have to use NCAP to anticipate upcoming OEM needs. The main differentiator at the industry level is going to be the ability to handle performance, along with applying the appropriate level of safety and security. Looking again at the NCAP example, being able to respond to NCAP requirements ahead of time and anticipate the need with more robust, safe, and higher performance solution will improve time to market. In emerging markets, for example, new car manufacturers are looking for quasi-turnkey solution to achieve the same level of safety that traditional OEMs are able to deliver. As a supplier to Tier 1s, we need to understand the system and the OEM needs. We have to define a robust safety concept upfront with the right features. The system solution combines safety and security. NXP has an excellent track record in functional safety and a very broad safety-related portfolio, going from sensor to power supply, battery management front-end, radar front-end, microcontroller, microprocessor, and so on and so forth. The NXP's Safe Assure program is in place since 2011. This program actually simplifies the customer experience and eases the integration of our component into the system safety concept. As mentioned before, NXP focuses more and more on system solution, including functional safety and security. This actually extends the scope of our, what I would call regular safety activities. We now have to cover from IP SoC, which was this original business, up to system, including also the software, and not only the basic software, but as well as the application software. Regarding the tool chain, it's then obvious that one tool chain cannot support the overall flow. So one of the biggest challenges that we have today is to easily interconnect and exchange data with our customers like system providers or even OEMs. Therefore, interoperability between tools become more and more important, especially between SoC, software and system, but also in between domains, like functional safety, SOTIF and security. As we said, it's three key things for NXP. On top of that, NXP also expands its competence and product portfolio in industrial, targeting the IEC 61508 standard for functional safety. So since more and more products will serve both industries, there is also a huge interest to bridge between tools, flows, and methodology between automotive and industrial, but as well as with medical, avionics, and so on and so forth in the future. As a conclusion, I would say that we believe that those challenges are not only NXP ones, but also challenges for the overall safety community. Thank you very much, and back to you, Alessandra.
Thank you, Franck. Last but not least, our next speaker is Bala Chavali from AMD. Bala is an SoC RAS architect, and as a principal engineer, she's driving her passion through technical innovation across many domains, including functional safety, embedded security, and RAS, reliability, availability, and serviceability. Prior to AMD, she worked at Intel and Texas Instruments, and she has over 50 years of industry experience focusing on safety-critical systems in automotive market with expertise in SoC and FPGAs. She's currently participating in Accellera as well as IEEE functional safety working groups. Bala, thanks for joining us, and you're next.
Thank you, Alessandra. Hello, everyone. Today, I would like to talk about SoC system challenges that are faced when performing functional safety analysis. It is essential to understand the target for the product safety markets, such as automotive, industrial, medical, avionics, and more. These markets define their safety levels and which safety standard guidelines must be met. Usually, when we refer to functional safety analysis, we mean generating FMEDA, failure modes, effects, diagnostics, and analysis, DFA, dependent failure analysis, or FFI, freedom from interference, or any other work products required by the safety standards. This analysis can be performed at various levels like component, system, SOC, or IP for both analog and digital components. Safety analysis requires complex and a large quantity of data, which needs to be gathered from various functions, such as marketing, technology, architecture, design, RTO verification, and validation teams. This data can also come from EDA tools, which perform synthesis, placement, routing, or RTO verification. Their output data is also an input into this functional safety analysis. This input data into analysis includes use cases, assumptions of use, specifications, safety requirements, failure modes, design and implementation hierarchy, safety mechanisms, diary of failure rates, coverage metrics, and more. Well, what are the challenges with this functional safety analysis? One challenge is the complexity. As the complexity of SoCs increase, the overall data size is increasing exponentially with both hardware and firmware. This challenge is also getting the correct data. Teams tend to lack safety background or safety standard knowledge and require training or hand-holding to extract the correct data required for the analysis. Therefore, information gathering and reviews consume plenty of time. Second challenge is completeness and reuse. This exhaustive data is present in various data formats and varies from team to team and tool to tool. This process of gathering this complex data and generating the right results has to be repeated multiple times over the product life cycle across desired markets for different safety standards. Next challenge is technical integration, which includes connecting IP and a failure modes hierarchy with enough abstraction to generate the analysis results. Well, do we need to connect this at this high level of abstraction, or do we need to break it down further? So when creating the safety analysis, every IP owner has to identify different failure modes, which leaves room for interpretation at SOC and system level for connecting these failure modes and their effects. Again, above is just a list of few of the common challenges that are seen. So, how do we try to solve these problems? First, we have to standardize the input and output data formats, both internally and externally. Standardizing this data format will increase data accuracy, faster generation of results, and uniformity across all results. Having a repository for failure modes, diagnostic metrics, failure effects eases the architecture and the safety engineers to compile the data faster and to generate the results easier. Another is to allow for interoperability between the IP, SoC, and system level data. So, Accellera Functional Safety Working Group is enabling two vendors, silicon, as well as IP companies to present their challenges, requirements, and use cases. Working group's goal is to produce a unified data format and concept and a language. This concept framework can be adapted at any stage throughout the safety lifecycle to produce various work products for the desired functional safety market. Thank you, everyone. I give it back to Alessandra.
Thank you, Bala. This concludes our presentations, and now we will take your questions for our panelists.
So let me see through the chat window. I think there's one question coming for Riccardo, actually. So Riccardo, if you are unmuted, I think one of the questions is, good, perfect. How big is the contribution of virtual platforms in automotive functional safety, and what challenges could be addressed by using the virtual fault injection frameworks?
Okay, yes, it's a very good question. So I will say that the virtual platforms are great, but mainly for concept definition into the way I see them, or for example, to start integration activity when not all components are ready. The side of the virtual platform that they have their own limitations, with in particular their accuracy. So how accurate they are with a real implementation. And potentially with this, we go to one of the most critical points today in safety in all the fields, that is requirements. How much are your requirements correct and clear? Are they semi-formal, formal? And in some cases, you end up, if the requirements are not perfect, that you specify something, your implementation, real implementation is doing something, the model is doing something else, and then you may have problems. So I will say the virtual platform are real important, but you need to understand what are the limitations. So you should really do some qualification, and there are kind of tools. So really confidence analysis, understand that how reliable they are, and consider what is the best usage. For fault injection, I will say they are great for fault injection if you want to, for example, check interaction between elements. I will not use this for fault injection to check coverage, for example, like a course F test. This I will not do with a virtual platform. But again, they have their own role in safety, and I will not discard them. I'm not sure if I answered the question sufficiently.
Thank you, Riccardo. I think if there are additional follow-ups, they can happen on the chat. And just if you're familiar with the DAC platform, you can always reach to the single individuals with follow-up as well. Okay, so there are other questions. There is a simple one to answer from Shrenik. The paper is going to be available at the end of Q3. That's the target for us on the white paper. And then again, from Franck, in terms of the public review, we are hoping to have a draft of the initial data format by the end of Q4. And that's what we are working on right now. So let me scroll up. There was, I think, more questions on EDA and combining EDA and safety from Selma. I think I'll answer very briefly on this one so that we also have space for more. But I think that the challenge is there's a big opportunity for EDA, right, to expand all of its strength into safety and just bring it as part of the flow. So make it like a functional safety aware flow as much as we have a low power aware flow and so on. The challenges are, I think, what we are actually trying to address in this group to find a common language. And when I say language, I really I'm not referring to a specific format, but to have a common language among all the participants. So, you know, it's a very interesting discussions. What we realize is that we all look at the same object from different angles, and when we talk to each other, it's obvious it's the same object, but we have very slightly different dialects about it, and it's important to nail out all those dialects so that we have a common language, okay? So that is some. The other actually part that is interesting for me more than a challenge is the opportunity to work on some of the methodologies, not only on the format, okay? So some of the methodologies that are out for safety right now might not be necessarily using, okay, all of the capabilities of EDA. And around that, I think I would like to also hear feedback from Franck in terms of the fact that beyond the main discussions that we are having on the format itself, a lot of discussions are popping up in terms of methodologies because they're still evolving. What you had mentioned, right, the freedom from interference, you know, the fault injection part that also came out during this discussion. So methodologies are evolving. Franck, would you like to elaborate a bit on that?
Yes, if you can hear me. That's
yeah,
okay.
We hear you well.
Okay,
yes.
Great, super, perfect. So, yeah, I mean, you're right. I mean, methodology is also very important, and just trying to define the format right away. If you don't have a good methodology, I think it does not make sense. So, for some of the functional safety area, then we have a good methodology already, so we can already think about the format and standardize the format. As you mentioned, fault injection is a place where I believe that we should develop a methodology, and not only about methodology how to inject the fault for analog or digital, but also the overall fault injection scheme, I would say. So from the top, really from the OEM or the system to down to the IP and so on, and to avoid that we are running actually fault injection at a certain level, and that it's not really useful to the next level, and they have to redo again. So this is the type of methodology. I see also a lot of things moving on, and I feel like things were moving on around the safety analysis as well. So you mentioned everything around interferences, or let's say common cause failure, dependent failure analysis is one. But I would also see maybe new safety analysis in the future, combining hardware and software. So having maybe an FMEDA and on top of it a kind of a software layer on top of it to really understand what is the probability of having a failure, which will really be critical, not only because it's in the hardware, but because this is a piece of hardware used by a software, especially in the microcontroller, for instance. So, yeah, I agree. I mean, methodology is a key thing that we have to work out as well.
Thank you, Franck. Let me read. There is an interesting question about the FIT and SPFM. As I read it through, I had one point that I think was brought up during the presentation, and that is actually one of the hot topics on our discussion is configurability. Ghani, do you want to elaborate a bit more on configurability, how it affects, you know, the communication interfaces, interlayer and intralayer?
Thanks, Alessandra. So there's two aspects to configurability. I think Alessandra pointed out. One of them is when you're doing your design for safety analysis and safety reporting and the different output and format like FMEA and FMEDA and DFA, those are based on a particular concept, safety concept. Now, when you shift the safety concept because of design parameters, for example, whether it's a design of use or some of the assumptions about the design, the safety concept is different, correct? So everything you have done in the past, today, it's required by the standard. They have to repeat the work. This is what the standards say. Once you move to a context or a different use case, then pretty much now you have to do your analysis based on the use case. Now, it doesn't mean that you don't have to use any or reuse some of the information you have generated for a previous use case. But at the end, you have to make sure that what you're doing is specific to that use case. So you can't just blindly copy. You have to do an analysis to make sure what is common, what is not. And for the easiest way is to start all over again. Now, when we have, if you are a company that are delivering for multiple contexts, that becomes you're duplicating your effort or triplicating your effort, depends on how many contexts you are using. So really, you have to make sure that there's a method of doing that, correct? And today there's no definition of it, because pretty much most of the people that I know, at least from my side, is that they take it as a different concept, and they do the entire, whether it's an FMEA, DFMEA, FMEDA, FDFA, they start all over again. Is there a way that we can improve that? I'm sure there is. And this is, I think, fall in the methodology. Somebody has to say, okay, what is the method? Like, for example, even in ISO, there's a concept of reuse, correct? For example, if you have an IP that has been used in the past, there's a concept, if you prove that that IP have never been, its context have not changed, or the context changed, but in a very minor way, defined way, you can say, I will reuse that IP and its analysis without any additional systematic satisfying of the systematic requirement of the standard. Same thing, we're trying to see if there's a way that we can do that for configuration of the IP. Now, I talked about how do you pass this information also to your customer, because usually a company, when they're developing an IP, they cannot generate all possible configurations. They cannot do the safety analysis on all the possible configurations. They do it on one or two just to convince themselves and their customers that yes, this is how you can generate the safety data. This is how you prove the SPFM and the LFM value or the SIL values and so on. Now, if the customer decided to change the parameters in the design, what is the responsibility of the customer at that point in time? Do they take the design from the IP provider as is, and then regenerate all the safety analysis needed? That's impossible, because to do an FMEA analysis, you have to understand the design inside out. And if you are a SoC integration company, you have between 100 to 150 different IP. There's no way you can repeat that level of analysis. So what is the requirement in this case? What is the requirement of the IP provider, and what is the requirement from the SoC integrator to do, correct? Because each one of them have to do a piece of it, and not both of them can have to repeat the work. So again, defining on what is the responsibility of each is something we believe that this Accellera group can help resolve in the future.
Thanks, Ghani. There is one question actually on the FIT and SPFM, as the FIT and SPFM estimate for IP and components can vary widely based on usage. And this is something that I think Riccardo also brought up. Does the information from IP upward need finer granularity that lets an integrator compose FIT for the subsystems automatically, or does this expose too much confidential data? Now, that's a very interesting point. And does the working group see opportunities for a language that can communicate the FIT based on different assumptions of usage, or does this become too huge of a problem to solve? Bala, do you want to take this one?
Sure. Hello. Actually, this is one of the main areas we've been trying to focus as part of the working group, is how do we, as part of an FMEDA, or as part of the, whether it's ISO or IEC, how do we standardize all the different data inputs so that we output the data such that, whether it is at an IP level you're looking at this, or at the SoC level you're looking at this, or at the system level, all of them have a visibility into data that is very, very standard, or so that we are able to make sure that we can communicate from one level to the other level. And one thing that we, as we've talked to so many different people, and as we're trying to get this, is number one is to standardizing that, right? We have to standardize this not just, from one layer to the other layer, which is what we're calling the interlayer. We also have to do this across interlayer, meaning that within an IP to another IP, we have to make sure that there is certain data format and certain data inputs and outputs, that we can have the common terminology, what are the common inputs that are present. So once we have that, now transporting that information from the intra layer to the interlayer becomes much more simpler. And the other place, you know, as I think the question is you're asking is it going to be exposing too much stuff? And that's the other balance, right? Is when we are calculating the data, yes, we'll have all the parameters, all the different configurations, all the different use cases that will allow us to get the FMEDA results that will have this SPFM, LFM, and the general fit. But the thing is that what parameters do we actually expose at that layer? So we are actually having to look at what is considered to be internal, what is considered to be external, and how do we make sure we have configurations that allow us to balance this between the internal data versus the external data. Hopefully that answered your question. If not, you know, please.
Thanks, Bala.
Yeah.
Yep. One quick question I can answer, your security. So there are actually quite a lot of activity on security. There is another Accellera working group, the IPSA, IP Security Assurance Group, that has, you know, activity on that area. As I mentioned at the beginning, there is also in the IEEE 2851 an effort to kind of connect security and safety and safety for AI. So there is also some activity there. These are the ones that I'm most familiar with, but then there are also some specific standards. I don't recall, honestly, the numbers of the standards off the top of my head. We can look it up offline. I'm not sure, though, if they focus on other security. So, and the other point here is that they are connected. We know that. And so after we kind of get first milestone under our belt, we do plan to work with the other entities and with the Accellera IPSA group on how can we actually combine the efforts, how can we talk to each other, not, you know, as people, but as standards. So there are activities and efforts on that area, and they are not disconnected from safety, of course. Very quickly here also, there's a question on whether there is a plan to bring in some software under this scope. I'll answer some and then I'll ask for questions also to the panelists, but the idea is to include it in the scope. One point here to reach out to the community is a lot of the focus has been for our team so far on the IP component level, IP SoC level. And we are welcoming anybody that wants to join, and we are especially looking for feedback from, you know, for also system level companies. So if there is anybody interested in joining, we could use that expertise, but yes, the goal is to bring in the software part as well. I don't know, Franck, do you want to comment a little bit on this? Is there anything more that you'd like to say?
What to say more? I mean, yes, we would like to include software. As you said, it's not easy because most of the ISO, to be honest, is even the ISO 26262 is very much related to hardware and system, and the software part is actually pretty close to a spice. So, but I feel like we need to do something. I mean, at least in NXP, we go more and more to a system solution, as I said before, and then we see really the need to connect more hardware and software together. And not only in terms of, let's say, checking the fault, let's say the diagnostic coverage of a core self-test or something like this, but it's also, we are also looking at how do we, let's say, consolidate the worst case execution time as well, like Jyotika mentioned for avionics. We are more and more looking at this for automotive as well. And this is why we need to have hardware and software together. And then I'm pretty sure that we have to exchange some data and some data format between both. Also, if we talk about more and more about this emergency operation, you know, we have for the autonomous driving, we're going to have to deal with that. We're going to have to deal with degradation concept, recovery concept on the fly, and so on and so forth. So here it's not anymore a question of hardware. It's hardware and software together. And this is why I believe that we have to connect both things together.
Thank you, Franck. I see one question about the impact of machine learning techniques, DNNs for perception or even planning control on functional safety. Is anybody that wants to give feedback on that? I don't know, Ghani, do you feel you want to say something on this, or anybody else?
Potentially I can give
a
comment.
Go ahead.
Here,
go ahead, Riccardo.
Of course, Ghani can comment after. But yeah, this is a big topic today about machine learning and artificial intelligence. the issue is not so much in terms of functional safety, or let's say ISO 26262, but it's more in the terms of SOTIF. So really how to ensure that the system with artificial intelligence is really delivering the performance and the functionality that you need. And that is today the biggest challenge. So we all know that machine learning, artificial intelligence is not really safe because it's not deterministic. But we all know that without this, potentially autonomous driving or some of the applications are not possible. So today we spend a lot of time to find really a solution, how we can really use this into automotive and functional safety. But yes, it's really a big topic. Again, as I mentioned, it's mainly to the term of SOTIF.
The SOTIF standard just came out recently, or is about to come out, right?
The PIS is already out, but there will be now the real official standard will come, I think within this year, yes. But honestly, there is still a lot of work to do.
Okay.
If I may add to what Riccardo has said, when you talk about machine learning and DNN, safety becomes very complex, because what is safety? Because if the design itself, let's say I'm an IP company developing the hardware, developing a hardware, and the software developing the software, and then you have the guys integrating the software and the hardware. It's really, to me, it's more like a thing at the system level, at the application level, because even from a functional perspective, nobody can prove that the DNN system or the hardware is correct by function. You're doing it with respect to a particular training set, correct? So when it comes to safety, I mean, I'm sure there's many people are working on it, and I think there was a mention. I think Alessandra mentioned something about the IEEE working group are covering the machine learning stuff. It's still early, and I think Riccardo mentioned clearly it's a SOTIF, but even in the SOTIF, is the SOTIF covering IP alone, hardware IP alone, and software IP alone, or the entire system? To me, it's still undefined. I mean, at least I know from an IP company, it's not that simple to claim that you have a piece of hardware that is machine learning hardware that is safe. There's no such thing, because I don't know what use case is going to be run on that I don't know what training set is going to be used. So till you have the holistic view of it, you can claim that it's safe, at least from a hardware perspective.
Thank you, Ghani. Thank you, Riccardo. There is a question very quick on if the scope covers analog and analog mixed signal. Yes, definitely that is part of the scope that we plan to address. One more point, which I think we hinted at a lot through all of our presentations, which is the traceability. I think we might want to expand a little bit on what are specifically some of the requirements with some real life examples on how it starts, how it ends, how it all ends up in the safety case. Bala, do you want to share some of your experience on that? Because I think it's more than just the word traceability, right? It's actually a lot of effort behind it.
Absolutely. So traceability, right? Even though it actually sounds sort of simple, when you talk about even just performing IP level traceability, right? What are we really talking about? We can be talking about traceability where we have a safety goal at the top, and the top as an item level. Then we have to talk about safety requirements sort of that come from the safety goal. And the idea is that as you go down from one level to the other, whether from the IP to the system to component, and component to IP, and even into each specific IP, right? We want to make sure that that safety requirement that actually is present, it's actually broken down, and that somehow we are making sure that we have implemented what we wanted to implement, and we have verified what we wanted to verify. So traceability, there are a couple of aspects. One of them being you want to make sure from documentation that all of that information is present. The other thing is that you want to make sure that you have implemented what you want to implement. And third is you want to make sure from a verification that this one requirement that you have specified all the way at the top, coming down to verification, to validation till the time the product is out, that you have done the verification or validation and make sure that you capture the results so that, some auditor or somebody comes back saying like, I think it's not working. How did you write the test case? Let's, go check. I can just open up something as in like my test case or my results or a page where I captured all the information, show that these were my conditions and this is how I cross-checked it. So it's very simple, having a safety goal followed by safety requirement, but making sure that that safety goal has been spec'd, implemented, verified, and made sure that we have captured the results is, for me, traceability. And trying to do that for one requirement sounds simple, but as we have now simple devices from going from one core to like 32 cores, 64 cores, and even more, making sure that we have traceability and we can show that all these things are present, goes with what ISO 26262 is calling out for, as well as IEC and all the other functional standards.
Thanks, Bala. There is actually a follow-up question, which you might have already answered. I think with functional safety standard, how is traceability defined? Are the failure modes for a system? So I think if you want to just go over it quickly.
Yeah, sure.
I don't think it's just a failure mode, yeah.
It's not just for failure modes. It's there for the data, for verification, for coverage metrics. It's, and just to cover, it talks about for the hardware stuff, it's talking about software stuff, it's talking about system. So it's covering all the different work products, as well as all things such as software, firmware, hardware, as well as anything you plan to do outside, which in functional safety, we call them as assumptions of use.
Perfect, thank you. Let me see, I don't see other questions. I think we went already past time. So unless I see something else coming in terms of questions on the box, I think we are ready to wrap it up. Please remember to continue asking questions if you want till August 1st on the box. You can also reach out again to each of the people here through the DAC system, LinkedIn, contact names on the Accellera website. There are either general for Accellera or for specifically for Functional Safety Working Group. So if you go to the Accellera website, you'll also see some introduction to the group and more information there, also more information about membership. So please continue to reach out. At this point, I would like to thank everyone for your questions, the interest in the Accellera Functional Safety Working Group. And I think this concludes the DAC luncheon. And thanks again for joining us, even though there wasn't like a real effective, juicy lunch. Thank you so much.